Have you ever faced a really complex problem? One that makes you wish you had a smarter, faster way to break it down.
Oh, definitely. Like a tricky coding bug, or maybe wading through a dense research paper.
Exactly. Or even a daunting math challenge.
Yeah.
We've all been there, and often just thinking longer doesn't really make us any smarter.
Right.
Welcome to AI Paper Podcasts. We're the place where we unpack groundbreaking research, the kind that promises to change how AI models tackle these very challenges.
And today we're diving into a really exciting paper. It's called rStar2-Agent, Agentic Reasoning Technical Report. Comes from Microsoft Research.
Yeah, and it's a massive collaborative effort. People like Ningxiang, Yifei Liu, Yizhu, Lina Zhegan, Wei Zhangshu, Xinyu Guan. Lots of brilliant minds.
A whole team. And they're tackling a core limitation in how today's large language models, approach problem solving.
The big idea. It's about moving beyond just thinking longer to genuinely thinking smarter. See, currently, many advanced LLMs rely on something called long chain of thought reasoning. It's like this meticulous step-by-step internal monologue.
Which is impressive, don't get me wrong, but it often hits a wall, right? Like when subtle errors creep in, or maybe the model needs a completely new angle, a creative approach.
Exactly. It's like planning a trip meticulously step by step, only to realize halfway you're on the wrong continent, and that internal monologue isn't helping you find a new route.
That's a good analogy.
But here's the game changer, the rStar2-Agent. This paper introduces an approach training a smaller model, just 14 billion parameters, to achieve frontier-level math reasoning.
And not by generating endless thoughts, like you said.
No, it's by developing these advanced cognitive behaviors. How? Through agentic reinforcement learning.
Which basically means teaching the AI to think smarter by autonomously using external tools, like a calculator or a coding environment.
And the efficiency is just, wow. A 14B model trained in just 510 RL steps over 1 week.
1 week.
Achieving 80.6% on AIME24, 69.8% on AIME25. That's outperforming much bigger models, like the 671 billion parameter DeepSeek R1.
It's pretty stunning, and what's really fascinating is that this isn't just about math scores. It shows strong generalization to other complex tasks. It really hints at a paradigm shift.
So the key innovations, you've got this efficient RL infrastructure.
Right, and a new RL algorithm they call GRPO-RoC.
And a really smart multi-stage training recipe.
Exactly, maximizing compute efficiency.
So what does this all mean for the future of AI? For how we tackle complex challenges? You're about to find out how these innovations push the boundaries of AI reasoning. Let's unpack this.
Let's do it.
Okay, maybe let's start by setting the scene. We've seen incredible progress in complex reasoning lately, right? Models like OpenAI's O-Series, DeepSeek R1, Gemini 2.5.
Definitely, and a big part of that has been approaches like test time scaling and that long chain of thought you mentioned.
Yeah.
Models generating really extensive internal reasoning steps.
Often fine-tuned with things like RLVR, reinforcement learning with verifiable rewards.
That's right. But the challenge is this thinking longer method, it has fundamental limits. It really struggles with subtle errors, those little mistakes in intermediate steps.
Or when you need a completely different line of attack.
Precisely. The model's internal self-reflection often just isn't enough to catch its own flawed initial path. You end up with these long, rambling solutions that are ultimately wrong.
It's like that brute force puzzle-solving idea. Just trying every piece instead of stepping back.
Exactly. And you get stuck down these rabbit holes.
So the vision here is to move past that, to enable models to, think smarter. Giving them the ability to autonomously use the right tools, check their steps, learn from feedback.
And that's where agentic reinforcement learning, or agentic RL, comes in.
Okay.
Instead of just that internal monologue, the model actively interacts with tools in a specific environment. It adapts its reasoning based on the feedback it gets.
And they chose Python tools specifically.
Yes, Python coding tools and an interpreter. That was the environment. It massively broadens the model's action space.
Letting it explore more. Verify steps.
Exactly. It allows for exploration of alternatives, crucial verification of intermediate steps, things that internal CoT really struggles with. It complements the internal thinking.
This thinking smarter vision sounds great, revolutionary even, but I bet getting there wasn't easy. What were the main hurdles? The unexpected snags in scaling this agentic RL?
Oh, you're absolutely right. There were significant roadblocks. A major one is what they term environment noise.
Environment noise.
Yeah, think about it. When an LLM generates code, it's not always perfect, right?
Definitely not.
So incorrect code throws errors from the Python interpreter. These errors can actually misguide the model. It ends up wasting compute cycles fixing code bugs instead of focusing on the actual reasoning problem.
Like getting confusing directions when you're already lost. Just adds to the chaos.
Exactly. And then there's the reward system itself. Current RL often uses outcome-only rewards.
Meaning it only gets a thumbs up if the final answer is correct.
Right. Which sounds simple, but it's deeply problematic. It can accidentally reinforce really low-quality reasoning paths.
How so?
Well, a model might generate messy, incorrect code, make lots of intermediate mistakes, but if it somehow stumbles onto the right final answer,
It still gets rewarded.
bingo!
Right.
So under standard approaches, we saw models getting the right answer eventually, but their internal process, their tool use, was still full of errors. Messy. Inefficient.
It wasn't learning to be cleaner, just luckier sometimes.
Yeah.
Not real intelligence.
Precisely.
Okay, so an AI constantly calling external code, getting feedback, debugging. That sounds like a huge logistical nightmare on the back end, the infrastructure needed.
Yeah, the infrastructure challenge is massive. This is where their engineering really had to shine. You're talking tens of thousands of concurrent tool calls per batch.
Wow.
You need a super robust, reliable, responsive code execution environment. Standard RL rollout methods just get amplified in their inefficiency here.
Just running Python locally would melt the CPUs, right?
Oh, absolutely. Overwhelm CPUs, leave expensive GPUs sitting idle, and it's even a safety risk. LM-generated code can be unpredictable bugs, infinite loops, you name it.
All right, let's dig into how they solve these problems. Starting with Edition 1, their Agentic Reinforcement Learning methodology, GRPO-RoC. It builds on GRPO, Group Relative Policy Optimization.
Yeah, GRPO is the foundation. It's an RL algorithm. It samples groups of reasoning paths, trajectories, and optimizes the AI's policy to maximize an objective using estimated advantage from those group rewards.
Okay.
And crucially, rStar2-Agent sticks with that outcome-only reward, binary 0 or 1 for the final answer.
Which is key for math problems with integer answers, stops the model gaming the reward.
Exactly. Prevents reward hacking, which is a real risk with more complex reward schemes.
So they keep the simple outcome reward, but they tweak GRPO itself to encourage more bold exploration.
Precisely. They made some important changes. One was removing the KL divergence penalty.
The KL divergence penalty, that usually keeps the AI sort of close to its original programming.
Yeah.
Like a leash.
That's a good way to put it. They essentially took off the leash. This lets the model freely explore really novel, tool-augmented reasoning patterns, stuff far from its initial state.
Okay, freeing it up. What else?
They adopted a clip-higher strategy. This relaxes a constraint on how much the model can change its behavior in one go. It helps it explore those high-entropy, low-probability tokens.
Which often signal those moments of self-reflection or trying something new.
Right, those crucial forking moments for creative reasoning. And finally, they got rid of the entropy loss term to stop the training becoming unstable, which can happen with aggressive exploration.
That sounds like a powerful setup for exploration.
Huh.
But let's go back to the environment noise, those messy but correct solutions. How does GRPO-RoC handle that without complex penalties?
This is where the resample on correct, the RoCe part, comes in. It's really quite clever.
Okay.
They acknowledge that adding explicit step-level rewards or penalties for tool errors, it sounds intuitive, but it adds complexity, needs human tuning, and risks that reward hacking, especially early on.
So RoCe avoids that.
Yes. It filters out the low-quality, noisy trajectories without using explicit penalties.
Elegant. How does the resampling actually work then?
Okay, so first, they oversample. They generate more rollouts than they need, say, twice as many, maybe 32 instead of 16.
Got it. More to choose from.
Then they asymmetrically downsample. For the negative samples, the ones that got the wrong answer, they just uniformly pick some. This keeps the variety of mistakes, which is good for learning.
So it learns from different kinds of failures.
Exactly. But for the positive samples, the ones that got the right answer, they apply a filter. They only keep the highest quality ones.
And highest quality means?
Minimal tool errors, good formatting. They calculate penalty scores. There's the tool error ratio, how many tool calls failed.
Okay.
Interestingly, if there are no tool calls, it gets a small penalty anyway, just to encourage tool usage.
Clever.
Then there's format for format violations, like redundant reasoning blocks. The total penalty is a total. Positive rollouts are then sampled inversely proportional to this score.
Meaning the clear, more efficient, correct solutions are much more likely to be picked for training updates.
You got it.
And this RoCe strategy, it really worked.
Made a massive difference. You can see it in the results. It significantly cuts down on coding tool errors within those positively rewarded trajectories. The naive GRPO approach just plateaued on errors.
Wow.
Yeah, and this directly leads to better reasoning performance and, importantly, shorter, more concise answers. It really shows models can learn to adapt to their environment, becoming genuinely smarter, not just luckier.
Okay, so the algorithm is smart, but Agentic RL at this scale, it also needed that specialized infrastructure you mentioned. It's not just the brain, it's the whole nervous system supporting it.
Perfectly put. The complexity, multiple turns, varying lengths, tons of tool calls. It just blows up the usual RL infrastructure bottlenecks. They pinpointed two major ones they had to solve.
First was the massive concurrent tool calls. A naive approach is too slow, too risky.
Yeah, their solution. A reliable, high-throughput code environment. It's distributed across the CPU cores of their huge GPU cluster.
So not running on the GPUs themselves.
No, on the CPUs associated with the GPUs. Think of it as a highly parallelized, sandboxed engine just for handling code execution safely and quickly.
Keeps things isolated, efficient, safe.
Exactly. And it's incredibly fast. Handles up to 45,000 tool calls per sec. The average latency from dispatching code to getting a response back, just 0.3 seconds.
That's blistering fast for that volume.
It is. And they even offload the answer checking, which is CPU heavy, to this service so it doesn't block the main RL rollout process.
Smart. But what about the rollouts themselves? Some short, some long, GPUs sitting idle.
That's the second bottleneck. Highly imbalanced multi-turn rollouts. Static allocation is terrible for this. GPUs finish short tasks and just wait for the longest one in the batch. Wasteful.
And you mentioned KV cache overflow.
Right. Imagine the GPU's working memory, the KV cache. If you stuff too many long, complex reasoning paths onto one GPU, its memory overflows. It has to discard data and recompute it later. Huge waste of time and effort. Leads to GPUs sitting idle.
Okay, so static allocation is bad. How did they fix it?
With a dynamic load-balanced rollout scheduler. It's clever. Instead of fixed assignments, it assigns new reasoning requests based on each GPU's current available working memory.
Dynamic allocation based on real-time capacity.
Exactly. Each GPU works independently. Tool calls get dispatched immediately, asynchronously, no waiting.
And as memory frees up,
the scheduler assigns new requests in real time. It keeps the GPUs busy and minimizes that cache overflow issue. Big improvement in utilization and efficiency.
it's fascinating how much engineering went into just making the learning possible at scale. Let's shift to Innovation 3, the efficient training recipe. They started with a Qwen 314B base model.
That's right. The goal was top performance, minimal compute, and their training recipe is quite different.
Oh, so?
Well, unlike a lot of prior work that uses heavy reasoning data in the initial supervised fine-tuning or SFT stage,
Right.
rStar2-Agent starts with non-reasoning SFT. The focus is purely on basic skills, general instruction following, getting the JSON formatting right, and basic coding tool usage.
So wait, the initial SFT wasn't teaching it how to reason with tools, just how to, speak the language of tools.
That's a perfect way to put it, exactly. Giving it the fluency to interact at all. They use data sets for function calls, instructions, chat.
Okay.
And the outcome was it got much better at using tools and following instructions, but its actual math performance stayed about the same as the base model.
So it didn't overfit on specific reasoning patterns early on and kept responses short.
Correct. It sets a clean slate for the RL stage to then cultivate the actual reasoning abilities more effectively.
Makes sense. Then came curating the RL data. What were the rules there?
Two main things. First, high-quality challenging problems with correct final answers, obviously.
And second,
Crucially, the answers had to be integers only.
why integers?
Avoids the nightmare of verifying algebraic equivalence. Is 2x plus 2 econ the same as 2x plus 1? That's hard for rule-based checkers and can lead to wrong rewards. Integers are unambiguous.
Practical. So they gathered tons of problems.
Over 100,000 candidates from places like DIPO, Art of Problem Solving forums, Project Euler, then clean them meticulously down to about 42,000 high-quality verifiable pairs.
Okay, data ready. Then the multi-stage RL training with GRPO-RoC. gradually increasing difficulty.
Yes, and crucially, gradually increasing the allowed response length. That's key for efficiency. They start shorter than other methods.
Which one?
Concise training, max response length set to 8K tokens. The model started short, around 1K tokens average, and gradually increased to about 4K.
Did it hit the limit often?
Initially, yeah, the clipping ratio rollouts hitting the 8K limit spiked for a bit, but the model quickly learned to be more concise.
And the results?
Huge gains on AIME24-25, jumped from basically 0 to 72.1% and 64.2%. Massive leap.
Wow, just in stage 1, what next?
Performance started to level off, so stage 2. Increase max length to 12K. Average response length climbed from 4K to 6K.
More room to think.
Exactly. Yielded consistent improvements on AE up to 77.0% and 64.8%.
And the final push? Stage 3. Focused on harder problems.
Correct. By then, many problems were too easy. They filtered down to about 17,300 harder ones, reset optimizer states, updated the reference model.
Like a focused drill session?
Pretty much. This further boosted performance to that final 80.6% on AIME24 and 69.8% on AIME25. Average response length went up again to about 8K.
And all this, the whole RL process.
Just 510 RL steps on 64 MI300X GPUs in 1 week.
Yes, and those are often just as insightful. For instance, they tried overlong filtering, basically, just throwing away rollouts that hit the max length limit.
Seems logical.
Counterintuitively, it made things worse. It actually increased the number of overlong responses.
Really? Keeping those truncated rollouts but giving them a negative reward acted as a useful signal. It taught the model to avoid repetition and be more concise.
Huh. Okay. What about detecting repetition directly, like n-grams?
They tried that too, penalizing correct rollouts if they had repetitive patterns, but it actually hurt performance.
Like, repetition seems bad.
It's hard to tell bad repetition from good repetition sometimes. Is the model repeating itself uselessly, or is it thoughtfully running similar tool calls to verify a result? Hard to distinguish automatically.
So the big takeaway on training seems to be about the reward design again.
Exactly. Keep it minimal. Final answer, correctness is best. Handle the other stuff, environment noise, formatting issues, maybe even conciseness through the RoCe sampling strategy, not direct penalties. It reduces bias, preserves exploration, lets the model genuinely learn.
Okay, let's talk results. The numbers here are just astounding. rStar2-Agent 14B achieving competitive math reasoning.
It's state-of-the-art for its size class, absolutely. This 14B model matches and flat-out surpasses much larger, heavily trained models.
Like on AIME24.
80.6% accuracy. Better than OpenAI's O3 Mini, better than DeepSeek R1, better than Claude Opus 4.0 according to their numbers, and 69.8% on AIME25, 52.7% on HMMT25. These are top scored.
Now, this is largely driven by the Agentic RL, right? Minimal SFT contribution to the reasoning itself.
That's the power, yes. Yeah. The Agentic RL is the engine driving performance from near zero baseline scores up to these heights with just that light non-reasoning SFT prep. Compare it to models without RL, like DeepSeek R10, and rStar2-Agent is substantially stronger.
It really highlights the cost effectiveness. Light training, less compute, huge results.
Exactly.
What really jumps out is not just the accuracy, but the efficiency. Thinking smarter with fewer tokens.
Absolutely. Higher accuracy, shorter responses. On AIME24, rStar2-Agent averaged around 9,300 tokens. DeepSeek R10, over 14,000.
Wow, significantly less.
It shows it's not just guessing better, it's reasoning more efficiently, using tools more intelligently. That's a direct result of prioritizing those clean, high-quality solutions via RoCe.
And the generalization, that's fascinating. Trained only on math, but performs well elsewhere.
It is really interesting, strong generalization. On GPQA Diamond, which is a science reasoning benchmark.
Okay.
Accuracy jumped from 42% after SFT to nearly 61% after RL. That actually surpassed DeepSeek V3 on that task.
So the math reasoning skills transferred to science problems.
It seems so. The core patterns learned from math seem effective for general scientific problem solving. That's a huge implication. And it held its own on other tasks, like tool use benchmarks and alignment tests, too.
So the Ablation Study comparing GRPO-RoC to plain GRPO really nailed its value then.
It did. First, Agentic RL with tools clearly beat non-tool QA methods. No surprise there. But then comparing GRPO-RoC against vanilla GRPO with tools.
RoCe was better.
Consistently higher reasoning accuracy and significantly shorter average response lengths. It really validates RoCe for managing that environment noise and pushing for efficient reasoning.
They did mention observing an upper limit, though. Performance saturation.
Yes, that's an important observation. After reaching peak accuracy, performance eventually saturated and even started to collapse slightly.
Why?
Their hypothesis, and it seems plausible, is model capacity. RL might be great at honing the reasoning skills the base model already sort of has. Beyond that inherent capacity limit.
So if that's true,
Then efficiently reaching that ceiling with minimal RL compute becomes the name of the game, which is exactly what rStar2-Agent demonstrates.
this research also gives us a cool peek inside the model's head, doesn't it? Analyzing those high-entropy tokens, like seeing how it thinks.
It really does feel like that. High-entropy tokens often signal moments of uncertainty, exploration, self-correction.
And they found two key patterns.
Right. First, forking tokens. These are seen in regular COTI models too. Moments where the model pauses, reflects, but wait, or let me double check, or maybe decides to rerun something. Increases the chance of catching errors.
Okay, so that's preserved. But there was a new pattern, specific to agentic reasoning.
Yes. This was fascinating. Reflection tokens on tool call responses.
Meaning?
When the model gets feedback from the Python environment, success, error, or whatever, it generates sequences of these high-entropy tokens. It's analyzing, interpreting that external feedback.
So if it gets an error, it stops and sort of thinks about the error message.
Exactly. Or if it gets a result, it might pause to validate it, compare it, maybe diagnose an inconsistency. It might explore alternatives based on the feedback, generate corrected code.
That sounds remarkably like, well, like how a human programmer debugs code.
That's a great analogy. It mirrors that human-like problem-solving loop. Act, get feedback, reflect, adapt. It shows these models are actively learning from interaction in a more sophisticated way.
That analogy really clicks. I remember trying to debug code sometimes, and the error messages themselves felt like part of the puzzle, almost like environment noise. It sounds like the model learned to navigate that too.
It really does seem that way. These agentic behaviors driven by RL incentivize this adaptive, environment-driven reasoning crucial for complex tasks. It's also just interesting that the actual Python code tokens the model generates are often low entropy.
Meaning it's pretty confident about the code itself, likely from pre-training.
That's the likely reason, yeah. Extensive pre-training on code makes generating the syntax relatively straightforward. The uncertainty lies in how to use the code, what code to write next, and interpreting the results.
All right, let's wrap this up. To bring it all together, rStar2-Agent isn't just another powerful math model. It feels like a genuine shift, right, towards smarter, more efficient AI reasoning.
I think so. The fact that a 14B model can outperform a 671B giant using a fraction of the compute and time, that's huge. It's a testament to the whole package.
Yeah.
The infrastructure, the GRPO-RoC algorithm, that clever training recipe.
It really demonstrates how teaching an AI to effectively use tools and learn from that interaction can yield incredible results.
Absolutely. And not just in math, but potentially generalizing across science, coding, maybe other complex domains. The researchers are planning to extend it, and they've released the code and recipes, which is great for the community.
It definitely leaves you thinking. If models can learn to think smarter by interacting with and reflecting on their environment like this, what really is the ceiling for their cognitive abilities? And, maybe more profoundly, how might this change our own ways of tackling complex problems?
That's the provocative thought, isn't it? Lots to consider there.